Now, I would now invite another very prominent thought leader and data scientist from Africa, Racine Ly. Racine, I would like you to come on the video also, because I think because of the bandwidth, I understood CS not trying to show the video, but if you can show what you are. CS, good to see you finally. You're a real person. Thanks a lot, Dr. Murthy. So I understood that the bandwidth was going down and all
Yeah.
a little bit. So I think you did the right thing by staying out, but appreciate that. And Racine is the director of data management, digital products and technology at Academia 2063. His research interests span the use of geospatial data and predictive modeling to study challenges at the nexus of climate variability and food systems in Africa. His work is oriented towards developing, adopting, and using technology to strengthen data driven decision making in governments for effective intervention and robust preparedness against climate shocks and uncertainties. He was previously the Africa wide research coordinator of the IFPRI, the International Food Policy Research Institute in Africa. Over to you, Racine.
All right, thank you so much, Parmesh. Thank you, colleagues, and thank you for the World Bank for having us for this very important webinar. So I'm going to present the work related to the Africa Agriculture Watch, which is the 4th program at Academia 2063. So the Academia 2063 is a non-profit international research organization. We are headquartered in Kigali, Rwanda. And we have a regional office for West and Central Africa here in Dakar, Senegal, where I am joining the call today. I would like to start my presentation with a few key messages that are related to the African agricultural sector and how it can be interesting to use geospatial information, in particular satellite data and AI in general. We know that the continental agricultural sector is facing numerous threats, and you name them. It's a poly-crisis setting between conflicts, extreme climate events, the health crisis. And what those crises are telling us is that there is a good planning that is needed, or at least to increase our preparedness to reduce the uncertainties in the decision-making process. Either it is at the policy-making level or at the farm level. We also understood and we believe that the conventional data gathering that we've been witnessing so far and the type of analytics might not maybe serve the purpose of combating the current crisis, how they are very different in terms of intensity and frequency. And that might not help us actually to have the level of details for an efficient and effective intervention planning. And here, the focus of AGWA is now to leverage two emerging quote-unquote technologies, such as satellite data and artificial intelligence. The former will bring the granularity, and the latter will provide actually the predictability approach in our case. The presentation is a 6-fold presentation, so I will start with explaining a little bit the anatomy of decision-making we are following, and then how we are trying to enrich the input data. I'm very glad that the previous speaker paved the way in terms of talking about the importance of remote sensing data in the agricultural sector. Therefore, I'm going to focus more on the predictability and what you can expect when you go and visit the AGWA platform. Now, our philosophy here is based on the idea that predictions will be at the heart of decision making. The next slide will talk about it more. But here, the pyramid that we're trying to follow is, let's make sure we can improve, for example, the forecast, the predictions that we are building in the agricultural sector. Therefore, it will help the decision makers to start strategizing and have effective policy making and the right outcome in the society. So the idea here is, how can we now support the decision-making process by making more informed? As a second aspect here, as I mentioned in terms of predictions, here is a simplistic way of modeling decision-making. It's not the only one, but it is one where, for example, you have to face a situation, and from there you need to collect the input data to have a good assessment, a stock-taking exercise, which is the input data aspect. And from there, you need at minimum 3 ingredients: the judgment, your predictions, and the training. While the judgment and the training are more subjective aspects because they depend on the decision or policymaker. Either it is a person or a system. But what we also know that is predictions can be improved in a mechanistic way trying to use models, and in particular, those that are emanating from machine and deep learning. Now, from there, you take an action and hopefully to have the right outcome. And then you have the feedback loops that will come and nurture the type of information you would consider in the near future when the time comes to take another decision. Now here, if you project this in the agricultural sector, it might mean that how can we now enrich the input data? Here, our approach is to use satellite data. And how can we improve the predictions? And here we are focusing on artificial intelligence in general, but in particular machine and deep learning. So this is the two aspects I'm going to show in the next slides, and then I will show what Agua does. Enriching the input data, here we start with the facts. When you look at the first panel about data availability in Africa, and you look at the second panel, which is the data capability index in Africa. So if you see the two graphs, you can imagine that there are some gaps between the two. We have the capacity to generate data, but the data is not available. Is it scarce? Is it collected and not available? That is another issue. But what these two maps is that there are issues that need to be solved. And the belief is that with the conventional, if we relied on the conventional, we would have been done with the data issue for a while now. Now, that's why we now rely on the satellite data and use those emerging technologies to reduce the gap. So going further down in terms of satellite data, what do we mean? So here it's a matter of using raw data satellite images and append additional analytics that allows to have a different story. If you look at the first column, there is a cropland area in Senegal, and the sub-image is the near-infrared image. So it's still saying a different story, but if you look at the well-known normalized difference vegetation index, you start seeing a different story about how vigorous the vegetation cover is. Therefore, you have a proxy to understand if there's a stress, either it is like pest and disease or it's like water related, for example. Another example of what another layer of analytics above satellite data can bring in is if you look at the second column where you have a true color satellite data from Sentinel. And now here, no one could tell you if it is wheat or sorghum or millet, everything is green. But if you use the spectral signatures of those crops and start doing some unsupervised classification, which is a machine learning technique, we start grouping those pixels by similarities. We don't know what they are, but at least we can group them by similarities and working with enumerators to have more information about what type of crop it is. And the last slide about, before the last slide on the use of satellite data, these are, for example, the type of signature of the light that crops or any object on Earth will reflect. So anything on Earth will absorb a part of the sunlight and reflect the other part. And here, if you have the way of measuring it, you'll be able to have the footprint, the DNA, how a signal that is specific to some features on Earth. So this is what is being used as well within the team to start building the data analytics related to agriculture and specifically crop types. Now, another example here is the vegetation index, but for two different regions. For example, the first panel is in a rural area that is known to also be a intensive cropland area, where in Senegal we have two main seasons, the rainy season and the dry season, and you can obviously see the cycle through the years for the first panel. But second, you can see also in urban areas like Dakar, where the signal is disturbed by the signatures of all the buildings and also roads. So this shows also that you can start having some more indication about what is on the ground and if you have an anomaly. For example, anomaly detection algorithms, seasonality shift, or the crop growth stage by using crop phenology metrics. Now, what we do us for Agua, here we collected the crop growing conditions. For example, land surface temperature, rainfall, and evapotranspiration. Those are information that we collect at the continental level, and not only for like a date in time, but it's a time series process where we take the data for the last 20 years and we start processing them in order to forecast food crop production. So these are our explanatory variables. In terms of the mechanic of the model, As any other model, there is a training and a prediction phase. The difference here in deep and machine learning is the type of function you're trying to estimate. It is an architecture with different other parameters you need to deal with. But here, the training phase is a data set that we use to train the model to understand the interrelationships between your crop growing conditions and your corresponding production from the historical perspective. Now, the machine will do an iterative process until it learns the relationship between the two. Once it is done, now you can use the model at the beginning of the season, feed it with the new data you get, the same that you use also to train it, and ask the model based on what you've learned so far, what are the predictions that I can expect with a certain level of accuracy. So I will invite colleagues here. We will share the presentation later to scan the QR code to access the publication related to the Africa crop production model. So at the end of the day, what do you get at the end of the process? So you will have access to a map. So so far, AGWA is covering 47 African countries and for 10 crops. So every year we follow the crop calendar, and then we provide those forecasts weeks before the harvesting period. Because, I mean, having a forecast after the harvesting period might not make sense because the data might be available. But here, what you get is a pixel level forecast that is more, let's say, disaggregated compared to the administrative level forecast that we used to see. It's an interactive platform. When you click on the pixels, you will have the value associated with those pixels, and they are forecast. As an example, on your right, you'll see the Mali 2023 forecast for millet. We also provide the same biogeophysical parameters that we use to build a model. And here you see the country on your left is Mali, and the blue area is where we are looking at. And we provide those data for the last 20 years. And it sort of helps to have an anomaly detection visualization where the green graph is basically the green line is the minimum for the last 20 years for that region, and the blue line is the maximum for the last 20 years for that region. And in between, you have the years. We also aggregate the information at a sub-national level, administrative level, for the policy or decision maker where the pixel level might be far reach. We compare 2 years and we look at the percentage of change between the two. So usually we compare the forecast of this year with the previous year. And we also have publications. So for every crop, every country, and any forecast, we provide a brief that is also open access on the platform. A 2-pager with the facts. What was the data last year? What do we have this year? What is the percentage of change? What can you expect in terms of increase and decrease by region and by department, in addition to the maps? We've been doing it also at the onset of the Ukraine crisis, where we wanted to know if there are alternatives and in terms of wheat, and also how to support, for example, initiatives like the AFCFTA, the Africa Continental Free Trade Area, we can benefit from it. And we did that for Morocco and the countries that are historically known to be wheat producers. And we've been doing this also during the COVID-19 crisis, and other publications such as scientific and those related to climate. The idea of AGWA at the end of the day is that from moving from raw data to knowledge and knowledge dissemination, there are some field level expertise that are required. And these are embedded within the platform that just provide the output for the decision maker to use it for strategies and policies. And these are, for example, from raw data to knowledge, those time series analysis and spectral band processing. This is being done with a team of around 10 people. And also from knowledge dissemination, also how to build a data-centric application for accessibility, interpretability, and sustainability. So what you can expect on AGWA in terms of products, they are like the community level crop production forecasts. You have potential agricultural land estimates. We are starting to work also on greenhouse gases emission measurement tracking, actually, and also crop type mapping. But I will show you the first results of the crop type mapping. So these are now the next steps, things that we are doing to improve the model and the process under AGWA. So crop type mapping is very important to Africa, and I think globally, because once you have it, you can also start looking at crop rotations patterns. You can start working with insurance company, for example. And here, this is the first results of a work that we've been doing in 5 African countries: Senegal, Ghana, Benin, Malawi, and Uganda. We introduced a probabilistic approach that allows us now to incorporate the mixed cropping common practice that we witness in Africa. Therefore, you can know that if you want a high level of certainty for a crop map, you might want to use the one between 80 and 100% of probability. Another aspect is here the drought risk and vulnerability. So this one is not like, this graph is not attached to just like the cropland areas, but the idea here is if we are not able to forecast what might happen in the near future with a certain level of accuracy or certainty, can we at least know where are our vulnerabilities? Therefore, when the crisis hit, at least we know where to position our faster response task force or intervention planning. So here we use a draw index and we append it or overlay it with a population density and build this typology where you know where are the areas where you might have a high draw and low population density as well. And here is an example of methane tracking, concentration dynamics of both croplands in Senegal using tropomy data. This is important also when you start looking at the nexus of climate change, climate variability, food crop production forecast, and also the food system. And we did that during the crop cycle where you have dry season, the sowing stage, the growing stage, and also the harvesting period. And we are working towards seeing how we can also discuss with local agencies to validate this work. And lastly, this is my last slide, where we start looking at also using AI to forecast climate parameters on croplands. We realize that our belief is that we have enough data now, or reanalysis data, and tools, either it is machine or deep learning, allows actually to mine the data and derive insightful information, rather than relying only on climate science and equations. Something could be done by combining both forecasts to hopefully have a better one. So here we try to do that for 1 pixel in Senegal. It's hourly temperature data. On your left, you have the comparison between the actual and predicted values, which is very dense because it's hourly. But if you do the difference in the middle, you can see that it's centered around 0, but with a small divergence between -3 and 3. But the histogram shows us to what extent actually those gaps are huge. Actually, they appear to be very small. And a difference between -1 and 1 degree at a local level is something we might accept for such a model. So the Agua platform is open access, therefore tracking it is very difficult. But we have feedbacks from countries that are calling sometimes to ask our forecasts and information. And most importantly, countries are requesting to have customized Agua versions here in the continent based on the data also that they would like to bring in on the training phase. I will stop here for now and looking forward to the discussions. Over to you, Parmesh. Thank you.
Thanks a lot, Dr.Racine Ly, and I think your presentation has given a lot of insights on what's happening at the continent level and what kind of capability and capacity really exists in Africa now to provide these services to the range of decision makers, users as we go forward. I think a lot of our teams from Africa listening in. I encourage them to get in touch with you so that when we discuss with clients, we should build this capacity of using this data and interacting with you to really develop the next level analytics when we take these decisions in various places. We have always a very good clientele from Africa in our webinars. So there are a lot of people who would come to you after this and they're asking questions. And I hope this will generate an very interesting community, which will continue to work with you after that. But I learned many new things. I think you brought the whole predictive modeling and remote geospatial data together and in a very application-oriented way. I think we will also disseminate some of your reports and results much more widely to our clients and also discuss with you how we can discuss this in a more systematic way as we go forward. Thanks a lot, Racine. As always, pleasure listening to you and get your perspectives. The next presentation